So this is, I just want to give a brief of the research activities, what we do there. So this is my group. One more person has joined this year, and this is the familiar face from here, from this college. And the one part of the group is working on electrochemical energy conversion. Hydrogen evolution, oxygen reduction reactions are important components when you look at the water, energy, hydrogen generation as well as in fuel cells. And then recently what I'm going to present is about urea oxidation, and then we also look at nitrogen and nitrate reduction. Nitrogen reduction for the ammonia process, to replace, there's an intensive research to replace the energy intensive Haber-Bosch process, which is the most commercially employed process to generate lots of ammonia, which is again a chemical for producing many other chemicals. So there is a great effort in that region. In that area, but nitrogen reduction we tried, but it's it was not really successful to produce percentage. But nitrate is a bit more promising than nitrogen. And then we also look at some photocatalysis aspects as well. Basically, when you look at this electrochemical energy conversion, especially with respect to hydrogen production, there are various aspects of it, not just generate hydrogen, then how to store it, how to transport it. There are various factors, but we are looking only at a small portion of it, which is the catalyst part, which helps to produce hydrogen more effectively, or transform other molecules to useful products more effectively. So only that part is going on in my group. So mostly in all materials or existing materials, how you can engineer or how you can modify to get a better properties. And then another interest is also in situ spectroscopy, again to look at the mechanisms of why it is not functioning or why it is so kind of aspects. And another, I think, this pointer is not working. So other aspect we look at is the diverse morphologies of metal oxides and composites, and we look at some easy synthesis routes. Initially I used to work with some liquid-liquid interface, which was actually started in Professor CeNS group to prepare metal nanocrystal films. So we initially we have used such simple methods to look at any lab you can make it actually, to get films of graphene, etc., and its composites. And recently we are also looking at other routes and these different morphologies, how it can enhance the properties with respect to surface enhanced Raman scattering, substrates for sensing applications, and then as well as energy. Another area of interest in my group is also some atomic force microscopy, using that whether we can look at the local properties of materials. You have a high resolution tip, which acts as the high resolution probe to look at different aspects of materials, but then you cannot look at any kind of material. It has to also be possible to put under that, and it needs to have a smooth surface as well. And what happened? So when it comes to it's moving, but the pointer is not. Yeah, hydrogen production, most people are familiar with the different routes of hydrogen production, like steam reforming. These are using the fossil fuels are the most common method even now to produce hydrogen, because that is the most established industrially. Anything to deviate from there, it takes effort and cost, which industry has to really think about putting some money into it. So still the methods heavily used are from the fossil fuels. And then there is an active research going on using microbial enzymes, the biomass conversion, and then there is this methane pyrolysis. And another one which we can consider as a sustainable route is the water splitting, where water is split into its hydrogen, oxygen, and very simple components, hydrogen and oxygen. And then in the the fuel cell, you combine them to produce again electrical energy, producing byproduct as water. So that's the kind of sustainable reaction here. And so the electrolysis has got interest in the past few decades. I mean, people have been working on it. It's not that it's a new thing, but and there are commercial electrolyzers, like based on what medium you use, what is the configuration of the cell. For example, alkaline electrolyzers, proton exchange membrane electrolyzers, and then now there is solid oxide as well as. So each one has different medium, like acidic or alkaline, and also its electrolyte and its catalyst. All of them have different components. And this electrolyte water splitting which I have shown is with respect to the alkaline medium, and the overall cell potential will be still 1.23 volt. And here, there are catalysts as on both cathode and anode, to effectively bring out. As you know, thermodynamically, it's not a favored reaction, splitting of water. So you need to really either do at higher temperatures or pressures, or bring about catalysts to split the water. And then you also need some potential, because it has this various potential to overcome, to have an effective evolution. So these overpotentials, or to bring the electrical application of electric energy and bring down the overpotentials, is the most research with respect to the catalyst. And in the commercial PM electrolyzer, the proton exchange membrane electrolyzer, the catalyst mostly used is platinum based. So there is some intensive thing, okay, the noble metals, as of now it's going on okay, but with time, like if you have more usage, then obviously the scarcity will come, and how you can replace this is another important area of catalyst research. And as I said, hydrogens, based on the way of production, it is categorized in various colors actually: black, gray, brown, blue, and green hydrogen. So it depends on what source, whether the source you use is renewable. For example, if it's a fossil fuel, it's not a renewable source, and so it cannot be considered as a green hydrogen. And then if the process produces carbon dioxide, which is not good for the environment, again, it cannot be completely categorized as green hydrogen. So based on that, it is categorized in various color codes. And the green hydrogen obviously should have, it should use the renewable source, as well as have less release into the atmosphere any toxic effects. So most of the fossil fuel base will come under gray and black kind of hydrogen, while if the electrochemical water splitting, if the electrical energy is coming from a renewable source, then obviously you can categorize it as a green hydrogen. But if the electricity comes from a thermal power plant which produces it is indirectly producing a lot of carbon dioxide, obviously you can't really call it as green, but maybe blue or something. And so I just want to say that, like in the alkaline electrolysis, for example, as I said, one counterpart is hydrogen evolution and other part is oxygen evolution. So this overall cell is minus 1.23 volt, and then once we if we can replace this oxygen, actually oxygen evolution reaction is a very sluggish, water oxidation is a very sluggish reaction, and also it requires a little overpotential to bring about this reaction. So if you replace this reaction with a urea oxidation, it has merits as well as demerits, and one can bring down the overall cell potential to minus theoretical thermodynamic cell potential to minus 0.37. And this is so this replacing the OER with the urea oxidation reaction, one can reduce the overpotential at which the urea oxidation happens, and it has other advantages, like it itself has hydrogen stored, and it's kind of non-flammable, and transporting urea is easy, and also chemically stable and highly water soluble. That is kind of one main merit is reduction in the energy demand for hydrogen production by reducing the input potential. And then another case is one can even think of a fuel cell where you use, for example, in the case of hydrogen oxygen fuel cell, where hydrogen oxidation happens and oxygen reduction happens, you can replace the hydrogen oxidation with the urea oxidation. And so the advantage is you don't need to use hydrogen, which is very difficult to store and transport. So that is another possibility in this direct urea fuel cell applications. Then another one is the environmental one can think of using the metabolic, we produce a lot of metabolic waste which contain urea, as well as industry effluents. Urea containing industry effluents can be used to again use for this purpose. So, but challenges, there are many challenges. The catalyst is low current density and stability, and of urea, it has a CO in it, right? So it will naturally, when you oxidize, it will produce some carbon monoxide, which poisons, it's a great poisoning on the catalyst surface. So that one has to look at when we use catalyst. And then if you are thinking about the remediation of urea, the wastewater, it's not only urea, it has various other components which may interfere, or else you have to think of purifying, which all adds to the cost. So these are the main challenges with the urea oxidation. And so this is what generally when you look at an electrochemical system. So first, there are many different characterization electrochemical analytical methods where you do a cyclic voltammetry to look at in how it progresses and what happens, etc. How is the current density, etc. So in this case, this is taken from the literature, one of the first major groups which have started this effort, and this is in the alkaline conditions between presence and absence of urea. So what happens here is there is a one can see when there is no urea, and this is using a nickel catalyst or nickel hydroxide. So what happens is there is a oxidation in the anodic, and then there is a reversal. So this oxidation corresponds to nickel 2+ to 3+ redox, and then when you add urea to it, you see that there is a very high enhancement in this anodic, which is actually due to the urea oxidation, and then followed by oxygen evolution. So the urea oxidation happens well below the oxygen evolution potential, and so this is what this is the region we are going to study for the urea. So people have looked at the mechanisms, how using in situ spectroscopic techniques, and in this case, basically it forms, even in the oxygen evolution also, it forms nickel 2+, it forms hydroxide to oxy hydroxide. So 2+ to 3+, and this then oxidizes the urea to its products, and then converts back to, this all happens in the forward potential, converts back to 2+ state. So the rest of the 2+, which doesn't go back, it will the reverse current, if it may go back to its 3+, whatever has not converted back in this reaction will go back to 2+. So and in the case of UR, there are two possible mechanisms are possible. One is direct and indirect mechanisms, where although the equations are similar, our potentials are lesser, for example, for the direct case, the cell potential. So direct mechanism is preferred, but most of the nickel hydroxide catalysts would show a combination of both the mechanisms, where this I will explain in the next slide. So so how to design a catalyst? So people look at the active sites to design a catalyst. There are various ways of looking into to improve the efficiency of a catalyst. One is to, if a catalyst, some metal oxide is insulating, then it will naturally cause higher over potential if you coat on electrode because of higher charge transfer resistance. So people improve the charge transfer resistance by combining it with other conductive materials or depositing as clusters onto porous carbon or other carbon-based matrices or some conductive matrices. So that can reduce our potential. So that is one way to improve the charge transfer resistance. Another way is to improve the surface area, because most the electrochemistry happens at the surface, and the surface act as the active atoms, so active sites. So if you can increase the surface area, you can improve the amount of active sites exposed. So that is another way of improving the activity of a catalyst. But then improving the activity of a catalyst, if you want to improve the intrinsic activity of a catalyst, one has to actually work on the active sites, how to increase the active sites in catalyst. So one uses modification of the catalyst surface to, in some cases we have found that, for example, in this case nickel 3+ has a much more activity. So how we can try to think in terms of improving the 3+ state in the compound, or one can think in terms of doping with other metals, heterometals that can dual kind of active sites. So these are the various ways of improving a catalyst design. So in the case of UOR, as I said, in the indirect UOR, what happens is the Ni3+, that's the Ni3+ hydroxide which forms, oxidizes urea and goes back to the 2+ state. While in the case of direct UOR, the 3+ form is quite stable, and it just activates, while oxidizing it doesn't go back, and it will have the same. So if you can stabilize this this Ni3+ ions through, then or increases tolerance towards carbon dioxide, as I said, you can improve the activity of the catalyst. So this is basically the various steps involved which people have derived from their experiments, where see the urea absorbs on the oxide hydroxide and gets dehydrogenated in various steps, deprotonated in various steps, finally producing nitrogen and carbon dioxide. There can be actually various reaction pathways, which I will show you in the last slide what's the importance of it. And so what our group has thought about is to increase a very simple way. Whether if you improve the 3+ states in the existing nickel hydroxide or oxide systems, how it will affect the urea oxidation efficiency. So this is what the work I am going to describe. So this is very simple catalyst, although the schematic looks very complicated. It's just nickel chloride and addition of alkali to form nickel hydroxide, and then to form nickel oxide it has been sintered at higher temperatures. And then to improve, in one case what we did is to improve the Ni3+ state. These were actually compacted into pellet form, and we exposed it to electron beam radiation to ablate the surface, and one could see a color change where it gets ablate. The greenish color will change to greenish black color, and only that portion was taken further to look at the So once you make a material, you have to characterize it, what is it and what it forms. Although we have some prediction in our mind, we need to look at it. And what we found is that in the case of in the case of nickel oxide, we got the standard pattern which corresponds to FCC structure of nickel oxide. And then in the case of electron beam irradiator, that's what we have changed it, ENIO. We could also see some peak corresponding to nickel, which was this peak nickel, and which indicates that although we are trying to form 3+, this is how it evolved, so indicating reduction of Ni2+ to nickel. But we should remember that this X-ray diffraction is a bulk technique, and so this has some nickel metal has formed. And we also looked at the transmission electron microscope and electron diffraction again to look at its morphology. We did not see any definite morphologies, like it's like usual crystallites what we got. And one can also look at the electron diffraction pattern to verify the, again we could see the nickel spots. So this is another, these are all supplementary, supporting techniques that will again tell the same thing, but it adds to the confirmation of the data, and this is mapping what we have done, elemental mapping. From there we can actually look at the atomic percent of oxygen and nickel in both the cases, before radiation, after radiation, and then we can compare to form this is under the TEM we have done, and we can look at the oxygen to nickel ratio. Here you can see that it's slightly higher, the oxygen ratio is higher and further we'll actually look at, this is not the definite way to look at it, but it gives some indication, and one can use more advanced technique like X-ray photoelectron spectroscopy, which is now actually a routine technique. This is a very surface sensitive technique. So what is there on the surface, what species is there on the surface, one can analyze through this method. And in this way, one can look at the particular binding energy where the nickel and oxygen comes, where high resolution spectra are acquired in that region, and you will see actually very broad peaks due to various metal ion species, and one has to deconvolute it to look at the different components, and so there are 2 peaks due to spin-orbit coupling of nickel, and then nickel 2p. And one can, when we deconvolute, we can see the 2 plus and 3 plus peaks due to 2 plus and 3 plus oxidation states. And one can, when we analyze them, the relative percentages, we found that in the case of electron beam irradiated one, it is the 3 plus ratio is quite much higher than the other case, the pristine case. And the oxygen also one can look at where is the lattice oxygen and the other defective site oxygen with lower coordination, and then the other hydroxyl groups on the surface. So surface will have hydroxyl groups on these oxides. So this can be deconvoluted further and look at the percentages also. So you can see that in the electron beam, the lattice oxygen, or more than the lattice oxygen, one can see the undercoordinated oxygen on the surface. So, so once we do the characterization, how we do the electrochemical further experiments. So you have a standard like a 3 electrode setup where you have a reference electrode, which is where you know the reference potential. Potential is fixed, that's why you use a reference electrode, and then you have the working electrode where we test our material or a catalyst, and then you have the counter electrode, which is again a standard electrode mostly we use. We can also use our material as the counter electrode as well. But in order to have initial performance parameters, we always take a standard counter electrode. So this counter electrode here, what we have used is the platinum, and then the working electrode, the catalyst we have to coat on something. So that working electrode is generally, we use something called a glassy carbon electrode, which is specially made carbon, which is very low resistance. So, this is to avoid contribution from the electrode resistance to the overall potential. And or one can also use carbon paper. So these are various working electrodes we use. Over that, we coat the catalyst of a particular loading. And then we perform the apply the potential and look at the current densities. So we use cyclic voltammetry to look at the current density, onset potential, surface, electrochemical active surface area, etc. Then you have this linear sweep voltammetry. Again, you look at the current density and the Tafel slope. And then the chronoamperometry is basically current versus time studies, which you can mostly look at the catalyst corrosion, whether the catalyst is stable or not. Then you have the impedance spectroscopy. Impedance spectroscopy, actually it's more complicated. Analysis is a little complicated, but it gives an idea about the chemical processes, and also the various resistances involved in the interface resistances involved in the reaction. So this is again coming back to NIO and electron beam irradiated one. We look at the CV. When we look at the CV, the CV cyclic voltammogram, without in the absence, there's no addition of urea here. We initially look at how is the 2 plus to 3 plus conversion in his case, and we can see a higher redox in current density with respect to 2 plus 3 plus conversion in the electron beam irradiated one. This is just the zoomed version to show you that here also you have, but but that's much lower compared to the irradiated one. And this is again the voltammogram, but this is a linear sweep voltagram with and without urea comparison in both NIO pristine and electron beam irradiated cases. So you add a particular concentration of urea. We also study with respect to urea concentration and choose a particular optimized urea concentration for this. And one can see that in this case you have if you look at the current density values here, it's much higher here, about 3 to 4 times higher in the case of electron beam irradiated one, where when you have the urea oxidation happening, which is also corresponding to the amount of 2 plus to 3 plus generated. And you have also the this is with respect to urea concentration we study. Like when you increase the urea concentration, you see an increase with respect to 0.8 molar urea, we see increase and then slight decrease, which is shows that it's a diffusion process. But after that it saturates, because once the surface gets coverage fully, it will not be active for the further oxidation. And then you have in the case of ENIO, you get the saturation at a much lower concentration of urea. And this is just, but if you see that even whatever the current density which you get for the higher concentration urea in NIO case, it's much, the ENIO case with 0.4 molar urea, the current density is much higher. So one can, from this we conclude that activity is quite higher after modification. And this is the Tafel slope, where you plot the O potential versus current density on the most active catalyst what you've seen. And in this case one can see that in the you see a lower Tafel slope for the beam irradiated one, which basically means that the kinetics is faster when you have a lower Tafel slope. And this we attribute it to the presence of more redox sites or active sites. This is again, I mean earlier also I had put, it's a various reaction pathways. So one can see that there is a urea adsorption, hydroxyl adsorption, as well as CO. Once it gets oxidized as the CO2 is formed, that also adsorbs or desorbs. So that process, urea adsorption, all these three processes are happening at one time, like when the reaction progresses. So these causes a competition in the active site, like gets blocked or released. And so in the impedance study, it has been established that when you have the carbon dioxide production as the rate determining step or the slower step, you have I mean you have the positive, the impedance, the real Z values in the positive direction, and as if you have it's in the negative real impedance values can be seen if desorption is a slower step. So this has been established by other pioneers in this field. I mean, like methanol oxidation, also you face this. And this is just again whatever I said, the same thing. Like if the rate determining step is CO2 production, you will see a positive real impedance, values. And this is two ways of actually presenting the impedance spectra. One is called the Nyquist plot and another is called the Bode plot, where Bode plot is like you apply frequency and you look at the phase angle of the AC impedance. And then in the case of Nyquist plot, it's a more simplified presentation where you're actually looking at the resistance. Its resistance is plotted. So you can actually read the resistance directly from the Nyquist plots of various processes. And so here, just if the CO2 desorption is the slow step, then you will actually see a negative real impedance values correspondingly also in the Nyquist plot. I think and this is actual one what we observed for nickel oxide and nickel oxide. We see that you have even in the case of the radiated nickel oxide in 1 molar kWh, we see that there is a predominant poisoning by carbon dioxide in the one can see these negative impedance values. So even at this these are done at various potentials. These potentials actually corresponds to the onset potential of your oxidation to until it goes. So that's the potential range we choose to look at the impedance spectra. And when it comes to we try to increase the alkaline concentration to see what it will have effect. We actually saw a great change when there is a 6 molar KOH is added to the current density drastically improved, as well as the Tafel slope also drastically decreased, which shows that the activity has been improved with same urea concentration but a higher alkaline. So the impedance actually studies showed that there is a reversal from when you add 6 molar KOH, you have a reversal of this negative impedance, the real positive impedance when you go to higher potentials. So that is where you have a better activity or better removal of carbon dioxide by having increase in the alkaline condition. So, but it will not work for all. It depends on the stabilization of the active sites and its tolerance, etc. So one can even look at, I'll skip the slide. Look at the mechanism of urea electrooxidation to some extent. You can't really establish it, but from the impedance spectra you can fit these equivalent circuits. And one component like the RC circuit is the simplest RC circuit, the Rundle circuit, and this there are two components we have fitted for the indirect UR and direct UR, and you look at the resistances involved and you get these values, and if you compare with the electron beam radiated and other pristine one, you get a much lower values of these resistances, mostly for direct UR in the case of ENIO, which shows that it has a huge, the resistance is lower means you will get a lower Tafel slope and good kinetics. So basically conclusion of this work is surface defective NIO by electron beam bombardment. ENIO shows strong interaction with urea than pristine NIO. And I'll just move on to the next one. So the another approach what we have used is instead of, there is another nickel oxide with Ni2O3 where nickel is mostly in 3+8, but of course it will have 2+ as well because this is the most, 2+ is the most thermodynamically stable state. So, and this was synthesized using a known method by oxidation with sodium hypochlorite. And we also looked at how the crystal structure and the typical crystal structure of Ni2O3 was obtained, but we could also see peaks due to nickel hydroxide as well in the Ni2O3. So it has, as I said, it's not a really thermodynamically stable phase, so it will convert back to 2+ to some extent. And this is again the electron microscopy characterization where we look at the nickel oxide crystallized as well as Ni2O3 sheets. And this again corroborates with what we observe in the X-ray diffraction. And this is again we looked at the X-ray photoelectron spectroscopy to look at the 3+ and 2+ ratio, and we as expected we got a higher ratio for Ni2O3. And also, so we also got, the oxygen corresponding to hydroxyl as well as in the Ni2O3, but much higher than NIO. And again, when we look at the UR oxidation, this is for the NIO and Ni2O3 comparison without urea. So one can see the 2+ and 3+, 2+ to 3+ is much higher in the Ni2O3. But in presence of urea, you obviously see a very much higher oxidation current due to the urea oxidation. This is the UR region and this is OER region. So it happens much before the OER region. And also in here, we do see a much higher, much higher this thing in the Ni2O3, but you can look at the current density values. This is almost 6 times higher than the NIO case. So we again attribute it to the more generation of nickel oxyhydroxide, Ni3+ oxyhydroxide. And we also, this is just a comparative curve to show how, to show the higher current density obtained for Ni2O3, and this is the Tafel slope also much lower we got for the Ni2O3, which shows a faster kinetics. And when it comes to again impedance spectroscopy, we look at the Nyquist plots, and one can see that there is a, in the case of NIO, you still use, as seen before, you see a negative impedance values, which shows that CO2 is a desorption is a rate determining step, which means that the poisoning is quite prominent, and this is also reflected as the phase angle values in the body plot. This basically both are same impedance in two different ways, but you get kind of different information you can take from this, because here you see actually a broad, broad peak, which is basically a convolution of two phenomena which is resolved in the body plot, which corresponds to, actually one can say that one is a direct and other is an indirect one. And once again in the case of Ni2O3, you see that CO2 production, you don't see much, reverse the negative impedance values in the case of Ni2O3. From there are some points, but we also looked at how many points are there. Those background calculation we also did, and we could say that the CO2 production is rate determining, that is desorption is much faster, and so it has got a higher carbon monoxide dioxide tolerance. We also try to look at the reason through DFT calculations. This was done by our collaborator Professor Ian Datta in IACS. So his student Jana actually looked at the adsorption of CO2, the urea molecule on surfaces as well as CO2 on the surfaces, and calculated the adsorption energy. So where you can see higher, charge density where adsorption is quite strong, and where you have lesser charge density adsorption is weak. So they have done an analysis of this Ni2O3 and NIO, how is the CO2 adsorption and the urea adsorption, and they found that even hydroxylation, they use the hydroxylation of OH adsorption as well. So the hydroxylation is much faster in the case of Ni2O3, and as well as also in the case of they derived the values from these calculations, and they found that the carbon dioxide adsorption is much weaker in the case of Ni2O3, while in the other case it's the other way around. And they also looked at the how the carbon dioxide is adsorbed, like what happens after the stabilization, and they found that carbon dioxide is a linear molecule, right? So it has been gone to the bond angle has been changed 164, plus the CO bond length has also slightly increased than the average value expected for it. So from this, we can infer that it's quite the adsorption is much stronger. The adsorption of carbon dioxide much stronger means poisoning is much predominant in the NIO case than Ni2O3, and correspondingly we see a better efficiency in the case of Ni2O3. And this is again once we do this catalyst study, but you also have to study how stable it is, or because one way of studying is to look at various potential cycles, how it withstands, whether the current density comes down when we run the potential cycles. Another way is to look at current versus time at a particular UOR potential. You look at the current density versus the time, and we can, at the lab scale, what is possible we do. 25 hours itself is like one day one has to monitor. And then people even look at, for industrial application, one has to even look at it much longer hours, and see whether they look at whether there is a degradation in the current density with time. So we see a much better case in the case of Ni2O3 compared to NIO. So that's where we have said that it is less, it's more efficient, and then we also do a after stability test characterization, how is the morphology, etc., which I have not shown here. And this is just a comparison of various catalysts. I think this is the concluding page. So it has higher OH minus and urea adsorption and better COX tolerance is the main inference from this. Than NIO, and with better NI, that means Ni3 plus stabilized formed is quite stabilized and favors urea oxidation. So I just want to tell you that there is much more to this to look at. There are various reaction pathways possible, not just nitrogen. People have also said it can over-oxidize to form nitrate, which is not good for the environment. So whether this has to be looked at in a different way, whether even along with nitrogen, whether this is being produced, and what is the oxidation pathway, what are the intermediates formed. These are the, a few people have done it, but one needs in situ spectroscopic techniques to look at these intermediates and what we can, whether we can utilize these intermediates to form other useful things. So operando techniques, and then people also look at nitrogen labeling to see the mechanism happening in this case. And then if we want to look at urea electrolyzer, it's even more, we do in a lab scale with 3 electrode setup, but the actual electrolyzer has only 2 electrodes, and one has to see the actual potential developed with respect to the current density and operational current density and cell voltage, and whether it actually, if you want to really look at the energy reduction, you have to do with the 2 electrode cell and see the the amount of electric energy required when compared to the usual hydrogen HER or OER kind of cells. And then if urine, people have shown using urine, but urea oxidation current, but it needs more if you want to apply in the real case. So I would like to thank, this is our club, Professor Ayan and Jana. He was my colleague and even at JMC, so he helps us with the calculations, tries to understand what we are trying to do and our inferences and see what they can do. And this is a Safir, who is alumni of this college. And part of this work I have presented from him, and he will be actually finishing this year. And Alex is the main person who has started the electrochemistry work, and others. And I would also like to thank my always mentor, Professor Kulkarni, and then our present director, Professor BLV Prasad, and the funding, as well as we have a central research facility which is also open to everybody. Others, based on some nominal charges are there. So that Professor Kulkarni has established, saying that we should open up our instruments to everybody. Yeah.
Thank you, Neena John, for the excellent presentation. We shall have 1 or 2 questions. Quick, please.
A nice talk, and the way that you are taking up hydrogen is very interesting. Globally, there is a lot of interest in the context of urea.
Many industries are approaching us, like.
Yes, so I wanted to ask you, and country as a whole is also looking at hydrogen. So is this urea a potential source? Can it really meet the challenges of hydrogen today? And if that is not the case, what is the more sustainable hydrogen source that you can look at?
Urea has a great potential, but I cannot say for sure, because we need to do a little more with respect to an actual electrolyzer. So that is one of the projects we have been trying, because when we project it to others, they will obviously they will ask, what is the energy reduction you get? But theoretically we can say 50%, 60%, but if one can prove that there is a really energy reduction, input energy reduction, and bring down, then do a cost analysis, because industry is always, okay, what is the cost of hydrogen per kg, can you say, if you use urea? So without that, it's very difficult to comment on that, whether it can replace the water, actual water oxidation, because water oxidation electrolyzers are now commercially there. But then, you have the catalyst problem, other problem. Here the main one disadvantage, demerit, is the carbon dioxide, which nobody likes. But then one can dissolve this in the, we are using alkaline solution. So one can remove this reduce flow, it dissolves in the potassium as potassium carbonate, and you remove it. as and when it goes. So,
There is another side as well. The urea is needed for agriculture.
yes.
Right? And this competition between energy versus agriculture
yes.
is going to put you into a deeper trouble.
Yes, that is where we suggest whether can we use effluents again.
Then this will not scalable.
But urine is quite, a lot of metabolic waste which is just going here and there. So if you can, try to tap it, but I cannot really comment on that in the present stage. Unless you do something in it, very difficult to comment.
Sure.
We are running short of time. So we will have more interaction at the tea time, I think. We shall move to
By the way,
next
Safi
speaker.
joined us an internship student, and then, so you should explore such options.
So please give a good applause to Dr. Neena Sindhon. Please accept a token of love from us, please.